Hello everybody, and welcome to Chapter 9, video lecture of Chapter 9. In this chapter we will be covering the subject of conservation of mechanical energy. There are two chapters in a row, Chapter 9 and Chapter 10, where we will be solving similar problem to the ones that we have solved in the last 4 or 5 chapters, Newtonian physics. But we're going to be using the method of energy to solve those same problems, okay? You will notice that the method of energy is more elegant, less steps, and you don't deal a lot with vectors. There are a little bit, but here and there, but mainly energy by its own nature is a scalar quantity. And therefore, you're not dealing with angles, you're not dealing with, whether it's the object's moving to the right or to the left, where to put the minus sign and all that. We don't deal with that. So it's a little bit, in that sense, a little bit more elegant, less hectic, if you will. So anyway, before I begin, let me just explain the lecture for you very quickly. I want to talk about what we mean by the word work and kinetic energy. And also I am going to cover probably parts of Chapter 10 as we go along. But anyway, okay. So let me bring in my notebook here. So when we say the word work, work is defined as the integral of the force times dx. Okay? Let me put it in simple terms. For those of you who have taken high school physics, you probably be familiar with work in a simple way. Let's say this is a floor, okay? And I have a box here, okay? And I push the box from this position here all the way to this position here. So now the box is here. Here is the box. Okay. And when I pushed it, of course, I exerted a force, F on it. And the box moved the distance x. Okay. So as you can see here, I have done work. I have done work to push the box from here to here, right? This work is basically equal to the product of the force times the displacement. Okay, this work, if you look at the unit of it, it basically Newton times meter, which what we refer to it as the joule. Okay, and the joule is a unit of energy. Okay, so joule is a unit of energy. So work is work is a form of energy. Okay, now why do we use the integral? Well, the integral is for if you're dealing with something a little bit more complicated. For example, if I have, let's say, for example, I have a force diagram. This is versus x here. And let's say I have this curve where this force is described by this curve. The work done in this case, let's say from point A to point B here, okay, it's basically the area under the curve, right? Remember that? When you are taking an integral of something, if this is f of x, for that matter, it is really big f of x, which is a force as a function of the displacement. So this area under the curve, how would I calculate the area under the curve? Well, the area, if you remember from calculus, is the integral, excuse me, the integral from a to b, right, of the function f, or we call it, for this matter, we call it force, dx, which basically what we are looking at here. Okay, so that's basically what it is. The force, the work is the integral of the force dx. Okay. Now look what will happen. Let me go back to that formula. Work is equal to f dx, let's say from a to b. Now we know that the force is equal to ma, right? And the acceleration is dv dt. Okay? And we also know that v is dv, what did I say? v is dx dt, rather, sorry. Get the eraser. Sorry, I should have prepared that eraser. Oh, I can't do it with the mouse. That's silly me. I need to use this new thing. I get the eraser with the mouse and then I erase with the pen, if that makes any sense. All right, so we have v is dx dt, correct? So this means dx is v times dt. So what I'm going to do, I'm going to take this expression and this expression for the force and plug them all in there. So basically the work in this case is going to be from A to B. F is equal to m dv dt times dx, which is v dt. Look at the dt's cancel out. So I'm left with from A to B the integral of mv dv. Is that right? Well, what is that? Well, that's just when I integrate mv, it's like integrating integration of x dx. Well, what is that? That's 1/2 x squared, correct? So we have the same thing. So that becomes 1/2 mv squared from A to B, correct? So we refer to this expression here as the kinetic energy. Okay? The kinetic energy. So, and if I give it the symbol K, okay, K. If I give it the symbol K, so this can be written as 1/2 mv sub b squared minus 1/2 m sub a squared, which makes it k sub b minus k sub a. You see that? And that's equal to the what? Equal to the work. Okay? Now, what's the meaning of this expression? Okay? So let me write it down again. This is actually a very interesting expression. Work is equal to the difference in kinetic energies, in two kinetic energies. What's the meaning of that? Well, let me tell you. Let's say, for example, I'm riding my bicycle, okay? So I'm riding my bike, and I'm pedaling, okay? And I'm going at the speed, let's say, let me call it VA, okay? I'm going at the speed of, let's say, 10 miles an hour. Okay? Let's ignore the units for now, okay? Just for the sake of argument, just ignore it. Okay, so let's say I'm going 10 miles an hour, which is the typical speed of a cruising, a bicycle in a cruising mode. All right, let's say now I want to go a little bit faster, so I start pedaling harder, right? So what I'm doing here, I'm doing work. Work is like exertion. So I'm pedaling even harder now, and now my speed is, let's call it VB. Now it is 12 miles an hour, okay? Now I'm going 12 miles an hour. Okay, so what I have done work. So the work, as you know, is force times distance. Force times distance, sorry about that. In its simplest form, Fx. Another way of saying it is that it is equal to the difference between the two kinetic energies. In other words, the initial kinetic energy that I had when I was pedaling, and going 10 miles an hour, it would have been 1/2 mVA squared, where VA here is 10 miles an hour in meter per second, okay? And then later on, I have pushed on the pedal a little bit faster, and then I am going now 1/2 mVB squared, okay? The difference between those two kinetic energies is also equal to the work. You got that? That's the essence of it. This formula, this theorem is called the work energy theorem. The work dash energy theorem. More on it in a minute, okay? All right. Another thing. Let's say, for example, more on the work energy theorem. So far we have said that work is equal to Fx, and also work is what? The difference delta K, kinetic energy. Let's call it Ke. Okay? Here's a third one. Let's say, for example, I have a book. Here's a book. And it is, let's say, it's sitting on the table. Here is a table, and the legs of the table. And let's say the book is sitting at the height. Let's say this is the floor, and let's say the height is 1 meter. Whatever height you want. Okay. And then I have a bookshelf here. And what I do, I grab the book, and I lift it up, and I put it on the bookshelf. Here's the book now. Okay. So now it's sitting on the bookshelf. Now the bookshelf is higher than the table. Let's say that the book now is at the height. Let's say I'm going to call that height 1. Now it is at height 2. Let's make it 2 meters, whatever, okay? So what did I do? Well, I also have done work. So I have the book, it's at 1 meter up from the floor. And now I have grabbed the book and I lifted it up against gravity and I placed it on the shelf 2 meters above the floor, okay? So what I have done here, I have done work. Remember the work, we said it is force times distance. This matter, now for this case here, the distance is in the vertical direction, okay? Let's say y, okay, if I call it y here, this is x, this is y. So I can maybe call it force times y. And what is this force? Well, in order for me to lift it, I have to lift it with the weight of the book. If it's less than the weight of the book, I'm not going to be able to lift it, correct? So the weight of the book is the force here. So basically mg, so mgy. So the work here is equal to mgy. You see what I'm saying? So what I did, initially here, the book has a potential, we say that it has a potential energy equals mgy1. For this matter, for our case, is h1, I'm calling it. Let me call that y1. Doesn't go beyond that. Oh well. Okay, so that's mgh1. Okay, well, you can put the number there. That's potential energy 1. And the potential energy 2 here is mgy2 or mgh2. You can put your number, 2 meters, whatever. But the work is the difference between the two. So the work here is the difference between in the potential energy. In other words, it is mgy2 minus mgy1, and that makes it mgy2 minus y1. Well, y2 minus y1 is basically the height between the table and the shelf, if you know what I mean, h. So we can just call it mgh, okay? So that's another way of seeing work. So now we have 3 different ways. Here they are. We have work is equal to Fx, again, in its simplest form. We have work is the difference in kinetic energy. And we have work in the difference in potential energy. Remember, kinetic energy, we have just derived it to be 1/2 mv squared. And the potential energy is mgh, okay? Now, we define, before I go any further, we define something called the total mechanical energy. Okay? The total mechanical energy, big E, is equal to the sum of the kinetic energy plus the potential energy. Okay, look at the notation. I don't like to call it KE and PE and PE. The potential is big U, okay, and kinetic is K. Okay, just to simplify the notation. Okay, so the total energy is K plus U. Okay. Before I go any further, I want to talk one more thing about work in terms of vectors. Work as a dot product between force and displacement. Okay? And then we'll start doing problems. That's really basically what the chapter is all about. And then I'll spend the rest of the lecture time doing problems. Let me just check the... Okay. So we define work as the dot product between the force F dot R, where R here is the position vector. Okay? It's a position vector. And F here, of course, is the force vector. Okay? Let me show you an example of that. If I go to, well, Well, before I do that, let me talk about the dot product. I don't think I've covered it in my lecture this semester, but what is the dot product? Again, this is something that I'm sure most of you have studied it in calculus, but I'm going to go over it very quickly. And if you are having difficulty understanding that, go back to your calculus book and read about the dot product, or you can watch videos or whatever. But I'm going to give you a small explanation of what a dot product is. Okay, a dot product, as you know, any vector A can be represented with I, j, k, right? So you have A sub xi plus A sub yj plus A sub zk, right? For example, I have a vector A is equal to, say, 3i minus 2j plus, say, 5k, for example. That'd be a vector, right? Where x, y, z is basically x, y, and z. So, for example, if this is the vector here, so it is 3 is right here, and the negative 2 is somewhere down there, and then this is the way they meet those two, and then you got 5 is right here. Let's say it's right here, and so the vector would be something like that. Here is the vector. Whoops, it's not very good, but this, let's say this is the 5 right here. So that would be the vector A. You see what I'm saying? 3D. Okay, below the plane, below the plane XZ. Okay, and so on. Now in 2 dimensions, of course, I think I'm looking at our book. It's mainly 2-dimension, I and j. So if I have a vector, let's say 3i plus 2j, so that vector would look something like that. Here is x and y. So 3i 1 2 3 1 2. And the vector is right there. This is the vector A. I'm sure you know all that. Okay? Now, if I have 2 vectors, let's say this vector and this vector, let's say this one is B vector, and let's assume the B vector minus 3i plus 2j. Okay? That's the B vector. Okay, the dot product, we define the dot product, A dot B, and when you write that dot, it's a big, nice dot, not a little small dot, make it a big, nice, solid dot like that. Okay, it basically, you just write them like this, 3i plus 2j dotted with minus 3i plus 2j, and what you do, here is the rule. I dot I is 1, j dot j is 1, k dot k is 1 for 3D, and then you have I dot j is 0, I dot k is 0, and then you have j dot k is 0. Okay? So anyway, what that means, if you have only it's equal to 1 if the unit vectors are the same. If they're different, it's 0. Okay? Simple as that. So when I do the dot product here, you know, think of it like you're doing the dot product like that. You know, when you like multiply foiling, it's exactly like that. But look at it. You don't need to write them all. See, I dot I, well, that's fine. So that's going to be 3 times minus 3. I dot I is 1, so that's just 1. Got that so far? Now let's do I and j. They're going to be 0, so that's not going to work. We don't need it. We don't need to write it down. That's what I'm saying. And then 2i dot 2j dot minus 3i, that's also 0 because j and i are 0. So now the only one surviving is 2j dot 2j, which makes it what? 4, 2 times 2 times 1. So the final answer would be 3 times negative 3 is negative 9 plus 4, so that's just minus 5. So there we go. So the dot product is equal to minus 5. Got it? Okay. Same thing works for work. I'm looking for an example in the book. Just give me a sec. I believe he covered the dot product in terms of vectors. He didn't bring any example, did he? Okay. Maybe I'll just, I know I've given you some homework problem on the vectors, the vector form of the work. I'll come back to that, but you have, I believe, homework 11 and 12, or one of them. Let me take one of them. Let's say, for example, number 11. Okay, no problem, number 11. It says, calculating work done. He said evaluate. Evaluate the dot product A dot B. A dot B if. That's what's given to us. I'm going to do part A. They're just a little bit long, but they're not difficult. Just part A here. I'm not going to do part B. It says A is equal to 4i minus 2j, and then the vector B is equal to minus 2i minus 3j. Okay? Find the dot product. Okay, before I do that, there is one more thing I forgot to. The formal definition, okay, the definition of the dot product is this. A dot B, you need to memorize that, okay? Not just for this class, forever. So as an engineer, you need to know what the dot product is. Anyway, A dot B is equal to AB. Remember, I didn't notice that I didn't put vector notation on. This is a scalar value. Cosine the angle between them. This is the formal definition of the dot product. What that means, let's say I have a plane, okay? Here's a plane. And I have two vectors. There they are. Whoops. Vector B. And let's say this is vector A, then they look perpendicular, but they're not. And let's say this is the angle between them. Okay? The dot product between them is that. So, for example, I can, in other words, if I want to know what is the angle between, I'll come back to this question in a minute, but hold on. Let me get the dot product of that first. Okay. So we have here A dot B. So basically it's going to be what? Negative 8 plus 6, correct? That's minus 2. Done. Whatever the units are. Got it? Okay. Now let's say I'm asking you, what is the angle between them? Okay? What's the angle between them? Well, I can use this definition. A dot B is negative 2. And A and B, well, let me find A first. Well, what is A? Basically, the scalar value of A is this. I'm sorry, 4. Again, I'm going to get that stupid eraser with the mouse. I have to go, so it's a special, oh, there we go, it works, okay. Then back with the mouse. All right. And then we have here, if anybody knows, give me a quick tip how to switch easily to the eraser without this 4 steps. I would appreciate it. But anyway, okay, so what am I doing? So I want to find the scalar value of A, which is basically the scalar value. So that's going to be here, I can't think of a better word, 16 plus 4, so that just square root of 20. I'm going to use my calculator. I have it here. So that's a square root of 20, and so 4.47. So that's going to be 4.47. And what about B? B is going to be what? 4 plus 9, correct? So that'll be the square root of 13. Answer 3.6. Okay, so now I have gotten A dot B. Already, right here, I have gotten the scalar value of B and the scalar value of the magnitude. There we go. That's the word I'm looking for. The magnitude of A and the magnitude of B. So now, look at this. So I take this formula, cosine theta, just solve for cosine. That's going to be A dot B over AB. See that? So A dot B is negative 2 over A times B is 4.47. This is for A, the magnitude, times 3.6. And then I'm going to calculate that. So that's going to be 2 divided by 4.47 times 3.6. I'm using the calculator. And then I'm going to get negative 0.124. Just say 3. So cosine theta is 0.124. Oops, I'll come back to that. Okay, and therefore theta is the cosine inverse of that, right? And again, I use my calculator. And the answer is negative 80, roughly negative 83. Negative 83 degrees. And there we go. Okay? So basically, this is the angle between the two vectors. You see what I'm saying? Everybody see that? Okay. As a matter of fact, there is one thing that I forgot. The dot product, those you put an absolute value here and here. So you basically ignore that minus sign. So I can just safely ignore that thing. Okay, so basically, if I'm going to draw, I mean, that would be the formal definition. You put an absolute value there. I forgot to mention that. But just a little details. So basically, what that means, those two vectors. Let me draw them for you on the XY coordinate. Well, there they are right here. Okay. I need to. So go ahead and look at them, and if I have the XY coordinate. This is X and Y. So A says it is 4 and negative 2, right? Here, let me write them down again here. Is 4 vector. 4I minus 2J, and B is equal to negative 2I minus 3J. So if I draw that, let me draw the vector A. 4, 1, 2, 3, 4, and then negative 2J, negative 1, negative 2. So the vector is roughly right there. If I can do a straight line, there we go. Okay, this is A. And then B is negative 2. So that's negative 2, negative 1, negative 2 right here. And then negative 3, negative 2 on negative 2, negative 3. Sorry for the... there we go. And this is the vector B, okay? See this angle between them right there? This is 83 degrees. Got it? That's the angle between the two vectors. Okay, everybody see that? Okay, great. All right, let's do a problem. Go back to physics now, and I promise I'll do one more problem with those vectors and how it relates to work. I haven't even talked about that yet. But anyway, let me do example 9.1 before I do problems from the homework. Let me look it up. Oh, we have it in the book. I keep forgetting we have an ebook here. I'm supposed to show it to you. It is on page 211. Gotta be here somewhere. Work, it should be right there. There we go, right here. Okay, it says, look at this. It says firing a cannonball. It says a 5-kilogram cannonball is fired straight up at 35 meters per second. What's the speed after rising 45 meters? Okay. Now, when we read a problem like this, I immediately will say, "Oh, that's easy. That's free fall. I can use kinematics." Yeah, sure, you can do that. But we're not going to be using kinematics. We're going to learn how to use energy, the method of energy. So here's how it works with that. It up. There we go. Okay, so this is an example. Oh, I reached the limit. Okay. Anyway, so we have, what is it, 9.1. So what you have here is the rocket. Did it say a rocket? Cannonball. Okay, so we have a cannonball right here, with a mass of 5 kilograms. Is fired straight up at a speed v0, 35 meters per second. Okay, what's the speed? So it goes up. There we go, like that, at a height of 45 meters. Here's the ball. He's saying, what is the speed here? It didn't stop, remember, it just keeps going, but we want to find the speed right here. You got it? Okay, again, you can use kinematics, but we're not going to use kinematics. I'm going to use the concept of energy. Remember, energy, I'm going to write it down here, energy is equal to kinetic plus potential, correct? Sorry about that. This is the limit of the mouse. It doesn't go above that, and it's my stupid setting. So let me just go here. Energy is equal to kinetic plus potential. Okay. So this energy is conserved. What that means, the value of this big E here is exactly the value of the big E here. Let's call it E1 and E2. So let's say, because this is position 1 and this is position 2 here. Okay, that's the Cannonball here. Okay, so E1 and E2, E1 is equal to E2. You got that? Because of the conservation of energy. All right. So the way we're going to do it, we're going to say, what is the total energy? Oops, again, this is my limit here. How do I do this thing? I'm sorry, hold on. This better? Yeah. Okay. So let's say this is E1, and of course we said that it is kinetic plus potential. So, does it have potential here? The answer is no, because potential, remember, potential is what? Potential is mgh, and kinetic is 1/2 mv squared. Those are basically the equations, okay? What that means, if there is a height, there is potential. If there is no height, no potential. Keep that in mind. There is a height, there is potential. There is no height, no potential. There is speed, there is kinetic. No speed, no kinetic. Simple? Okay. So look at position 1 right here. When the moment that you projected the cannonball, well, it was at 0 height, so that means no potential. So it's all kinetic. 1/2 mv squared. This v is v naught, right? Because it's given to us. Okay, I'll come back to it in a minute. Okay. Now E2, which is way up there, right here. Okay. So we have kinetic plus potential. So let's kinetic plus potential. Do we have kinetic? Well, he asked for the kinetic, so therefore there is one. And that kinetic, I don't know what it is. I'm just going to say 1/2 mv squared. You see what I'm saying? Plus potential. Well, is there height? Yes, there is, 45. So it is mgh. mgh, where h is really this one. Okay? Now, how the E1 and E2 are related? They are equal. Equate them together. So I'm going to have here 1/2 mv naught squared equals to 1/2 mv squared plus mgh. The m's cancel out. That's why, oh, he'd still give me the mass, but I don't need it for now. And then he's asking for the v squared. So let me multiply. I need to get rid of this half. Multiply both sides by 2. So that's going to be v naught squared equals v squared plus 2gh. And then v squared in this case will be 2gh. I'm sorry, minus 2gh. You move it to the other side, it becomes a negative, right? You know, when you move it there. And then plus v naught squared. And then you just plug in your numbers. So the v here becomes the square root of all that. I don't need to solve it. And then you calculate and you'll get the velocity here. You got it? So as you can see, I have used the concept of conservation of energy to solve this problem. This is what you need to learn for this problem, for this chapter. Okay, one more problem. Let me do, as I promised you, the vectors, the work as a vector form. It's I'm trying to find, there is a couple of problems there. Oh, there they are. That's one of them. That is number 18, 918, 916, and 917. Let me do 16, okay? Maybe I'll do another one. Okay, let me go to, I think I can find it from here. Chapter 9. What number? 16. It's kind of pain in the neck trying to find it through this. Is that text? Yeah, okay, that's not bad. Is that the one? Yeah, there it is, right here. This number 16. Okay, it says, let me shift it this way. I have a limited screen view for the video, and that's probably the maximum that I could stretch it. All right, and then I lift this up. Okay, and the limit here, I can go as far as this much. That's it, before it disappears. All right, so here it says a number 16 here. Oops. He says a 25 kilogram air compressor, so we have mass of 25 kilogram air compressor, is dragged up a rough incline, okay, from R1 to R2. You see that? Okay, let me see if I can have them both at the same time, at least temporarily. So here I have R1. I'll draw the picture in a minute. Let me just put in the data here. R1 is 1.3i plus 1.3j. 2R2 is 8.3i plus 2.9j, where the y-axis is vertical. How much work does gravity do on the compressor during this displacement? So we want to know the work done. In other words, what is the force here? I mean, he's asking for the work. We know that, right? He's asking how much work done by gravity. What does he mean by gravity here? What does he mean by gravity? Gravity here means the weight of that box, okay? So the force here is really the weight. You got that? So he said, how much work is done by the weight? You got that? That's really what he's saying. Okay, let me draw a picture of this. So he says it is an air compressor is dragged up a rough incline from R1 to R2. Okay, so it's kind of hard to draw 2 dimensions, but I'm just going to go roughly something like that, just to give you a visual picture. Here is an incline. Here is the compressor. Okay, and here is the weight of the compressor. It's going to be a vertical line. There we go. It's good enough. Okay, and the work, he says the air compressor is being dragged, so there is a force on it. It could be a push or a pull, it doesn't matter. I'll make it a push. Right there, here's the force. It's being pushed like that, dragged, okay? And we want to know the force done by the weight, not by this one, by the weight, okay? Now, if this is mg as a vector like that, you can think of it like 25, the mass, g, the gravity, 9.8, right? And then what direction is that? Well, that's j. You agree with me on that? That'd be j. Okay. And the work is equal to, in this case, is F or mg. Let me just write it in terms of just a general form. F dot delta R. Well, delta R, basically the displacement, the difference between those two. Okay, so let me get delta R. Delta R is nothing but R2 minus R1. So in this case, I would have, you want to say 8.3 minus 1.3, which is what, 7? 7i, and then plus 2.9 minus 1.3, that'd be 1.6 j, and there we go, that's delta R. Okay, so in this case, work is equal to mg as a vector dotted with delta R. Okay, so mg as a vector is right here. I have that. Of course, it's 25 times 9.8. Okay, I'm just keeping it like that, but that's what it is. So 25g j dotted with this vector 7i plus 1.6j, and of course, because the dot product, j and I will go to 0, so you're left with j here. So that's going to be basically 25 times g times 1.6 j dot j, which is 1, right? And then this, of course, 9.8, so 25 times 9.8 times 1.6, and then you get the answer. And oh, one more thing I forgot. Of course, it's going down, so that should be a minus sign, right? This j is negative. You see what I'm saying? Sorry about that. So that should be a minus sign here. So it's going down, right? Negative. So this is a minus right here, and that's a minus. And then you will end up getting the answer. Let me use my calculator. Negative, if I did it correctly, negative 390 joules. Of course, it's a scalar value. This is a scalar value, right? It's not a... The dot product always produces a scalar value. And there we go. This is how much work. He said, how much work does gravity do? I mean, how much work is done by the weight during this displacement? The word displacement, basically delta R. You just take the two vectors and get their difference. You know what I mean? Okay. Number 17 is very similar to it, so I'm going to leave it to you as an exercise to do. Actually, a little bit different, but anyway, I don't find it difficult. I'm just kind of looking at it from my book here. And then let me do number 18. I think it's homework as well, but I'm not sure. Number 18 on the homework in the end of the chapter. Okay. Oh, it's right here. Okay. That's good. Okay. You see this table right there? This is the one we're going to do. So what I have in here, it says you have a, I use my mouse to point. So here is the shape that we're dealing with. And we have here, he says, I'm sorry, I'm reading 18, and that will be, there we go. I'm reading this one. I'm saying number 18, I'm sorry, number 18. Okay, it says here, the two ropes seen in the figure are used to lower 255 kilogram piano 5 meters from the second story window to the ground. Okay? How much work is done by each of the three forces? Got it? So of course this is the weight. F sub g here is the weight. Okay, let me make a drawing of that. It's number 18. I'm sorry it's taking too long. Okay. Okay, so what we have in here, here's the piano. I'm just going to turn it into a box like that. And maybe these are the legs of the piano. Okay. And then I have two tensions. I'm going to call this T1. This is T2. He says T1 is equal to 1295 Newton. And T1 is 1830 Newton. And then we have the mg, he called it F sub g, I like mg. Mg, which is equal to 2500 Newton. Okay? And here is the floor. The piano has been lowered by 5 meters. That's basically the displacement. You got that? Okay. So all right. So first I need to get the work. Sorry. Oh, I need to go this way. I apologize for that. There we go. So I need to get the work as done by the weight, by mg. What does that mean? It means work F delta dr. This is the formal definition of the work, where F here is the weight. Okay, so force, work done by the force, specific force that way. So it's going to be mg dot delta r. Okay, everybody see that? Okay, so but he didn't give us any vectors for the delta r. Here is one way to see that. You can see it as a 5, negative 5j, or do you remember the definition of the dot product? It says a dot b is equal to ab cosine theta. So you can simply, what you could do if you have this expression, which that's exactly what we have, I can just say the scalar value of weight times the scalar value of the height, which is 5, times the angle between them. Well, what's the angle between them? Well, the weight is this way and the height is this way. The angle between them is 0. You see what I'm saying? So basically it's going to be mg r, which is the height, delta r, let me just call it delta r, times cosine 0, because it's just the angle between the 0. They're both parallel. So in this case, it's going to be equal to, the mass is 2,000, the weight, the whole weight is 2,500. Multiply this by 2,500, multiply this by delta, which is 5, and you multiply this by 1. Cosine 0 is 1, right? And then you calculate that. So it's going to be 2,500 times 5. Answer, you're going to be 12500 joule. Okay? The one right there. Okay? Are we done with that? Okay, now, the work done by tension 1. Let's go back to tension 1. Again, what is the work in general? The force dot delta R. For our case here, it is the tension 1 as a vector dot delta R. Okay? And delta R is, remember, it's lower at 5 meters, so that first is going to be 5 meters. So where is tension 1? Tension 1 is right here, right? I forgot to mention there is an angle here. Look at that. There's the angle right there. Hey, look at the mouse right here. Angle 60 and 45. So I need to put them there. This is 60, and that's 45. So now, let me go back. Now, while I solve it, look at this figure here, guys, okay? Look at the left here, right here in the figure. Okay, so what I have in here, tension here, remember, the force have to be parallel with the displacement. So we only take the component of the tension that is parallel with the displacement. So that's going to be T1 sine 60. You got that? T1 sine 60. So that's going to be, and of course, because the displacement, see here you have the displacement is going this way, the displacement. Remember, it being lowered. It's going this way, delta R. But the tension is going this way, the T1 sub x, the x and the y direction, excuse me. So they are opposite. In this case, the work would be negative, okay? So in this case, we would have minus T1 delta R. And of course, it is the T1 here sine. We're going to take only the y component, sine 60. That will give me negative 1830 multiplied by 5 for delta R. And sine 60 is 0.866. And then we calculate that, and we would get negative 7.92 times 10 to the third joule. Okay? Similarly, the work done by tension 2, here is tension 2 right here. So we're going to take only the y component of that, which is vertical, and it's going to be negative because the displacement is opposite. So it's going to be sine 45, right? So very similar to this one. So that's going to be something like minus T2 delta R sine 45, and that's equal to negative 1295. That's for the tension. Sine 45 is 0.707 multiplied by 5, which is for delta R right there. Okay, and then we calculate that, negative 4.58 times 10 to the third joule. Okay, that's it. Got it, everyone? Okay. One more problem. How much time do I have? Okay. I have two more. Maybe I'll do two more. They're both quick problems. Let me do number 30. Okay, number 30 right here. It says, a horizontal spring with spring constant 85 Newton per meter. So we have a spring with spring constant of 85 Newton per meter. Extend outward from a wall just above the floor level. Okay, let me show you a picture of how that looks like. So you have something like this. Here is the wall. Here is the floor. I have a spring. Okay, and here is a mass here. Okay, this is a mass, and that's the spring constant right there. And okay, he says a horizontal spring of spring constant 85, extend outward from a wall, there we go, just above the floor, 1.5 kilogram box, sliding across a frictionless floor, hits the end of the spring and compresses it. Oh, I'm sorry. So this, okay, so this is free box, and then it hits the spring, and then it compresses it. So basically, what happens later? You know what? This is not a good picture. Let me draw that picture better. I'll just take that. Okay. So what you get? Let me draw a better picture of that. So here you have a spring. Oops. I need to go back to pencil. Oh yeah. Okay. So here what you have a spring. Let's say you got something like that. Here's the spring just sitting by itself. At far away here, we have a box moving. Okay. So what's going to happen, the box is going to hit the spring and is going to compress it. So later on, so what's going to happen here, here is the spring compressed like that. And then you got the box right there, okay, compressing it. At the moment of compression, right, maximum compression. Okay. He said, extend. So 1.5 kilogram box sliding across the frictionless floor, hits the end of the spring right there, and compresses it 6.5 centimeter, okay? So this spring is not compressed. Now it is compressed by a 6.5 centimeters. Okay. Before the spring expands and shoot the box back out, how fast was the box going when the spring, when it hit the spring? Okay, so we have here a velocity like that. Okay. Before I do that, I want to tell you something about springs. Okay. Springs. So a spring, you know, so you have the force on the spring is called a kx, and there is usually a minus sign there, where this is called the spring constant. I don't like calling it the spring constant. I like to call it the stiffness constant. Stiffness. The larger the number, the stiffer the spring, okay? So it has to do with stiffness of the spring. And the x here is the displacement, or elongation, if you will. Okay, the compression or elongation of the spring. Okay, and that's basically it's called Hooke's law. This law, and this is the force on the spring. Force on spring. Got that? Okay. Now, remember we said that work is equal to the integral from a to b of f dx. Well, let me try it for the spring force, this spring force, right? So it's going to be something like minus from a to b, kx dx. So that will be basically 1/2 kx squared from a to b. Okay, let me ignore the minus sign for now. From a to b. So basically the work is equal to the difference between the two. 1/2 kx squared b, minus 1/2 kxa squared. Okay, that's an expression for the work. Of course, remember, this is a potential energy. So this is a potential energy of the spring. Potential energy of spring. Okay? So in other words, if I'm not dealing with gravity, okay, in other words, potential energy, gravitational potential energy, I can say that the total energy is kinetic plus potential, where this potential is a spring potential. I can do that. Sorry, kx squared. And this one, of course, is 1/2 mv squared. You got that? So I can use this expression, this version of the conservation of energy, if I'm not dealing with gravity. If I'm dealing with gravity, this E is equal to 1/2 mv squared plus mgh. Okay? So whichever fits your problem. So I'm going to deal with that for this problem. Okay? So let me go back and try to solve this problem. Let me move on to the next page. So in the beginning, the block was moving with some velocity v0. Here's the spring. Okay, so here if I ask the question, what is the total energy of the system before collision, before the block collided with the spring and compressed it, before compression? Well, E in this case, it was just the only energy available here, just the kinetic energy of the block. There is no, the total energy is 1/2 kx squared, but there is no elongation. It was just the spring was relaxed, or compression. The spring was relaxed, so there is no displacement. So that's 0. So the only energy that's available to us is just 1/2 mv squared. Make sense? Okay. Now after compression, at the moment of compression rather, here's the compression, here's the block right there. Now, of course, the block now stopped, so the V here is 0. So what happened is that all this kinetic energy has converted into potential energy to compress. Okay? So now if I go E equals 1/2 mv squared plus 1/2 kx squared, this kinetic is 0. There's no kinetic, it stopped, right? So it's only that. So in other words, of course, because the energy is conserved, that means this E and this E are equal. That means this quantity and this quantity must be equal. So I'm going to equate them together. So I have 1/2 mv0 squared equals to 1/2 kx squared. The halves cancel out like that. And then I'm asking for V0. So V0 is going to be equal to K over... I have a feeling that I'm going to sneeze, but I can't sneeze. Anyway, anyway, we have K over mx squared, all of that under the root. And then I just plug it in. So he says, if I go back here, he said the spring constant is 85. So that's going to be 85 over the mass is 1.5 times the displacement. He said 0.65, I think. 0.65 right there. So it's going to be 0.65 squared. Is that 0.65 centimeter? I'm sorry, 6.5 centimeter. That makes it what? 0.065, sorry, right? There we go. And then this is half. And then we calculate all of that. And I did this calculation. I have it in my note. If I did it right, it is 0.49 meter per second. There we go. Okay, guys? Okay. I think I'm going to stop here. And please let me know if you have any questions or if you want me to work on any other problem in the homework. I'll be more than happy maybe to. And by the way, if you have a question that has to do with homework, problems, anything like that, please post it under Ask the Professor in order for everyone to benefit from it. Not through email. I mean, I don't mind email, but we'll keep email for personal things. If you want to discuss something personal, like your grade or whatever. But if you have a question, any question that you think is going to benefit your classmate as well, such as homework or whatever, please post it under Ask the Professor. I try my best to check it every, at least once every 24 hours. When I wake up, that's the first thing I do. I check it. And if I see something there, I will reply to it as soon as I can. Okay? All right. You have a good week, and be safe and healthy. Goodbye.